The other type of laser which can be made to be single frequency, and it's very much used in optical communication system, is the distributed Bragg reflector laser, or DBR for short, right? So in DBR lasers you have two mirrors which are constituted using Bragg stacks or Bragg reflectors that we've just discussed, right? So you have an actual cavity here which is separated by two Bragg stacks. So the DBR would look more or less like this, right? You would have an active region. It would look more like a Fabry-Perot cavity in the sense that you have an active region and two mirrors on either side, except that the mirrors now are the Bragg reflectors. So you have one Bragg reflector on the left of the cavity here and another one on the right. So one on the left and one on the right, and the mode propagates between these two mirrors. So what I'm calling mirrors are the Bragg reflectors, and light propagates inside the cavity, inside the active region, between one mirror and the other one, just like in a Fabry-Perot laser. So therefore the cavity is formed in the region between these two mirrors, right? So, and the mirrors, because the corrugated structure can have many periods, these mirrors can be made to have very high reflectivity for the Bragg wavelength, of course, right? So only for that wavelength, depending on the amplitude of the corrugation, of course, and the number of periods, the number of repetitions, the reflectivity can be made much larger than for a simple Fabry-Perot cavity, right? But because the cavity now can also be made much smaller, right? So let's compare, the cavity of a Fabry-Perot again, right? The length of a Fabry-Perot cavity, which is hundreds of micrometers, to this length here, which can be made, to be 10 micrometers or even, smaller. This length here, the length of this cavity here, is much smaller than that of a Fabry-Perot cavity. DBR is much smaller than the length of the Fabry-Perot cavity. And as we've seen, the FSR, the free spectral range, right, the separation, the frequency or wavelength separation between the spectral lines, have an inverse dependence on the cavity length. So for a smaller cavity length, the FSR is actually going to be larger, and therefore, inside the gain region, in which the gain overcomes the losses in the cavity, if you design this cavity to be small enough, the FSR will be large enough that only one mode or one line will appear inside the gain region, right? So that's the basic idea. You can make a much smaller cavity in this way, right? So that's why DBRs can also operate with a single longitudinal mode. In other words, you can make single frequency lasers with DBRs as well. And DBRs have the advantage of being much more stable in terms of the emitted light frequency than DFBs. So here we have an optical microscope photograph along with SEM images of the active region, right, and the Bragg stack itself of a DBR, right? So you have the cavity here with the two Bragg reflectors on either side, right, here and here, for this DBR laser. Finally, the VCSEL, or vertical cavity surface emitting laser, is in a way similar to a DBR in the sense that you have a cavity or an active region with two Bragg reflectors on either side, but in this case, for the VCSEL, all of the layers will be deposited or grown on top of a chip. So you can imagine that you can actually make the Bragg reflector by alternating layers here on the surface of a chip, right, on the surface of a chip. So you can have all of these staggered layers, and then the active region, can also be deposited, and then you can follow this by an additional Bragg reflector on top of the active region, right? So all of these layers are deposited on the surface of a chip. So that's why it's a vertical cavity, because light is going to be emitted by the surface of the chip rather than by the lateral facets. And the double heterostructure is placed between two Bragg stacks, and the double heterostructure is placed between two multi-layer structures, right? So to have a more accurate depiction, you might have something like this, right? So you have the PN layers and the active region forming the double heterostructure, but the idea here is that the active layer is placed vertically on the surface of a chip between two Bragg reflectors, one on top and one on the bottom, right? So light propagates in this direction now, and on its path it goes through the active layer vertically now, okay? And usually, you know, you can have a bottom Bragg reflector which has a very, very high reflectivity indeed, and a top one which will let some of the light pass through, right? So the reflectivity at the Bragg wavelength can be made to be 90 to 95%, so that some of the light escapes through the surface of the chip here, right? And these will be metallic contacts. So the reflectors usually consist of alternate refractive index films stacked together, so these will look much more like the Bragg reflectors that we've discussed at the beginning of the lecture. And you can have as high as 20 to 25 periods per reflector, right? So you can have like 20 to 25 alternate layers on this reflector and on this reflector as well, right? The length of the cavity is usually around 10 micrometers. The length of the active region here, right, can be made to be, depending on the design FSR, of course. And again, right, this will determine the FSR, and therefore, you know, if you make a longer cavity, you might have a laser which is not single mode, a laser which has more modes, which supports more longitudinal modes, right? So since the length of the cavity is small, the cavity FSR is large, and the VCSEL can be made to oscillate with only one longitudinal mode. You know, again, light will propagate back and forth between these two Bragg reflectors here, these two mirrors, and you have a light beam because of the partial reflectance of this Bragg reflector here. You have a beam coming out of the top surface with a wavelength equal to the Bragg wavelength. An additional advantage of these types of structure is that on a single chip you can fabricate many, or you can fabricate an array of VCSELs, right? Because, you know, you can open holes at different portions of the metallization layer, and therefore you can make an array of vertical cavity surface emitting lasers. On the other hand, one disadvantage of the VCSEL is that since there is not a very well defined waveguide, right, because the structure is actually propagating back and forth on the vertical direction here, it do not have a very well defined waveguide. Some problems may arise related to the number of transverse modes, right? So the transverse modes now would have to look like this, but you might have more than one transverse mode, so engineers have to come up with ingenious ways in order to avoid more than one transverse mode, you know, in this direction. And also the field distribution of these transverse modes and the way it couples to free space might be an additional issue here, right? For all of the laser structures that we've discussed, temperature can be a very great issue, right? Because as we've said, the threshold current for all of these devices can vary a lot depending on the temperature. So usually the way to cope with this is to design the chip, the diode laser, which is illustrated in this figure right here, right? This would be the chip coupled to an optical fiber. Usually the chip is designed to be coupled or integrated to some sort of coolers, such as Peltier effect thermoelectric coolers, So this structure with the pillar shaped structure right here is the thermoelectric cooler, which is controlled by the light coming from the other edge of the chip, right? So for DFBs and DBRs, you can have light coming out of either facet of the chip, right? So the light that's coming out from the front facet here is the light that is actually being used, but you can also use the light coming from the back, right, in order to fabricate a rear facet photodetector. And this the reason for having this photodetector here is so that it can detect the fluctuations in power emitted light from the laser, and then actively control the temperature by some control mechanism of the thermoelectric cooler in order to maintain temperature stability, right? So this is one way to deal with this large temperature dependence of the threshold current of these types of lasers. Okay guys, so this was it for today's lecture. We have ended our discussion of laser diodes. On our last couple of lectures we're going to talk about photodiodes and photodetectors. So thanks a lot for your attention, and I'll see you around.